to this Tuesday seminar, and a special welcome to the many of you who are from outside the ABI today. So I'm very happy to present Dr. Pablo Gregorini from DairyNZ. So Pablo was born in Argentina, and he received a bachelor's in agricultural science in 1997. He then completed a MSc in nutritional ecology and physiology of ruminants in 2001. And moved to the US for his PhD at the University of Arkansas, which he got in 2007. He moved to New Zealand as a scientist at DairyNZ in 2008, and he's been there ever since. So he's received a number of awards through his career, including the New Zealand Large Herds Association Award in 2009. The Emerging Scientist Award also in 2009, and award for scientific excellence in 2010. So he has authored 55 peer-reviewed journals, 4 book chapters, and edited a special issue in nutritional ecology of foraging and grazing management for animal production science. He serves on the editorial board for the Journal of Animal Science and is an associate editor for Animal Production Science and Grassland Science journals. Pablo is actively involved in research and teaching. He has supervised 7 honors, 2 MSc and 3 PhD students, and currently co-supervises students in Lincoln University, Waikato University, and at the National University of Mar del Plata in Argentina. So I hand over to Pablo.
Okay, good afternoon everybody. Thank you for being patient, and thank you for being willing to listen to what I like to say. I'm being recorded, so I better behave. So when Dino invited me to give a talk about what I was doing here, and just to know that I was going to be in front of mathematicians and modelers and engineering, studying to say, oh man, what am I going to do? So I back up and said, well, I better talk from an animal scientist point of view, so I don't get hard questions from mathematics or coding. So even if you ask that, I'm going to say, I don't know. I work in a team, the modeling team of the Feed Farm and Systems group in DairyNZ. The team is composed by Pierre Buques, who is the team leader, Alvaro Romera, who is a system scientist. I'm the animal scientist there, and we got 2 programmers that deals with the coding and the math. So my involvement in my models is pretty much to develop them and create some kind of biological approach to the mathematics to reproduce what we perceive from nature. So at that year, I was finishing, well, I finished my undergrad a little bit early than 98, but that marked me. So by then I was starting to think, okay, well, as much as I like animals, what, from an agricultural point of view, what is the main factor that can influence performance or productive performance? And Eric and Larry, Eric Colbert from here and Larry from Penn State University were saying that herbage intake is the most important variable affecting animal productive performance and pastoral systems, right? So then I thought, okay, well, it seems like to eat grass is quite important. It's quite easy to think from a nutritional point of view of how much grass we need to give to the cows to produce X amount of milk. That's pretty much the amount of grass that the cow eats per day. So 19 kilos of dry matter. So it's obvious that she needs to do a lot of things to eat it and make it go through the rumen and excrete a little bit of that. And I'm going to be talking not only about process of ingestion, but digestion and excretion. And if we got time, how those things may have an impact on the environment, or footprint, if you like. So that's a sweet story. When I was doing my master in nutrition, so that's really easy. But reality indicates that it's not that easy when we talk about that process and the pattern of grazing, as you can see. Forage there is not presented in a nice pile of grass. So in those grazing environments, you know, we don't have control over the quantity they're going to eat, the quality of what they're going to eat, and when they're going to eat it. Simply because of three-way interaction between the plant, the animal, and I would say the rumen there. In addition to that, and because of the three-way interaction, the animal modified what it's eating. So the cows or any ruminant can start eating a particular sort that we think it got a particular quality, but as it depletes the herbage mass, it faces different qualities and different herbage availability. So the feed is more dynamic than the TMR served in a trough when we are talking about grazing environments. And in addition to that, the animals express the innate behavioral patterns. Because of that, in that particular process, there is intake of herbage. We don't have any kind of reliable means to measure dry matter intake, or herbage dry matter intake, if you like. Therefore, we believe that predicting it, describing it, and modeling it are critical for supporting research to improve management of herbage intake in grazing systems. I just put the picture of Pablo Picasso there because he's an artist, and sometimes you think that talking about all of that, require a little bit of artistic point of view, and he's got my name as well. So, having said that, and because the grazing process took me to New Zealand, imagine that if you do your PhD in nutritional ecology of foraging and grazing management, where would you like to be? In New Zealand. So that's why I got here, and I end up working in the modeling team. So I'm going to be talking about from Molly to Mindy, 2 models. So straight ahead, Mindy is the name of my wife. And new advances and opportunities for modeling processes like eating grass or eating herbage, and how that changed over time, the behavior of that process, the pattern in grazing ruminants, although I'm going to be used mainly a dairy cow as a model. So first, I'm going to be introducing you guys Molly, which is a cow model that was created by Professor Lee Baldwin from University of California, and how in DairyNZ we improve his version to the actual Molly version of DairyNZ. I'm going to spend some minutes showing the latest development in Molly, which may be of interest for Stephen and Bina. And then just show 2 examples of how we use Molly in the context of a whole farm model as a component model of that bigger model. Then start talking about the metamorphosis or the transition from Molly to Mindy. Talk about Mindy, who is she, latest development in Mindy, and some of the new modules that we add to Mindy in her development, so diet selection and preferences, foraging bioenergetics, and the Shasta outflow dynamics. So, as a way of introduction, we can say that in those particular environments, in vitro or in vivo, to have estimates or measurements at the same time or parallel of intake, ingestive behavior, rumen function, and metabolism pose, as you may think, a kind of a challenge for the scientists, and also economical challenges. It's quite expensive to take that many measurements at the same time with accurate enough and with good precision. Therefore, there are several technical limitations. Well, we can spend hours discussing about technicalities of estimated or measured intakes, estimating some behavior actions and strategies and patterns of that, and even more talking about rumen features, so the things we want to know about the rumen. So because of all of that, in those environments, in vivo and in vitro, advances in those kind of interaction has been slow and costly. And because of that, we are thinking of model. Model is a purposeful representation of reality, essentially a simplification of the system. So in virtualis or in silico, modeling allows us to quick and inexpensive evaluation of systems that can go from cell to landscape all the way up and down. Well, that's why I'm saying scaling up and down. Test our thoughts and hypotheses, and sometimes our theories, or develop theories using the models. I guess while you are modeling, somehow you are creating your own particular theory in a particular column of that particular system, if you like. In addition to all of that, models can also help us to make predictions and help farmers in particular situations, as we do in DairyNZ. And this is the purpose of these two models. One of them is already doing that, and the second one is on the way to do that. It's more like kind of scientific models that we could use to explore alternatives. But if that model has a purely represented or purely represent the reality, or that is a simplification, an oversimplification of the reality, I mean that system, the understanding and predictions of processes and the pattern of those processes get far from that reality. So you can wonder if the model is really useful for that particular purpose, having that clear. So going from MOLY to MINDY is pretty much that. We are trying to get close to the reality, as the picture tried to show. From simple empirical models that can predict intake to more dynamics and mechanistic models that can predict pattern of intake or other processes like urination or rumen fermentation. So MOLY, what is MOLY? MOLY is a deterministic and mechanistic dynamic model that represent digestion, metabolism, and production of a dairy cow, built up from aggregated biochemical pathways level. MOLY was built up by Professor Lee Baldwin. In fact, he started building up MOLY through the modeling of a sheep, the rumen of a sheep here in Palmerston North in Ag Research, when he was doing his sabbatical in '86, if I'm not wrong. Then he went for another sabbatical in UK, and together with Bieber and France, they built up, and they clustered those modules, digestion, metabolism, and built up MOLY, which is, in my opinion, one of the most sophisticated mechanistically and dynamically, if you like, models of a dairy cow or even of a ruminant. It's a whole cow rather than an aggregation of simple models predicting rumen function, for example, like other models that are floating around. This is a schematic representation of MOLY, quite simplistic, at least in my opinion. You can say you have the compartments in gray boxes here. You can have the rumen, and the rumen is composed by large, small particles and soluble matter. You know, from large you go to small particles through digestion and breakdown physically of those particles. And then when you got soluble matter, you know, it's utilized by microbes, and the microbes also digest small particles. Nutrients flow to the small or large intestines. From the rumen, large and small intestine, nutrients are flowing to the blood, and from the blood to the body, and from the body with the different tissues that you could read, fat and protein and fetal tissues, you know, and that through endocrinological regulations and visceral transactions end up in a product, milk, for example. But you could also take, you know, that the fetal growth as a product or fat as a product, if you like. Also some byproducts of digestion that, if you like, or you can take like excretion, urine, or feces. Again, that's an oversimplification of MOLY. Of course, this part of the story, the feed, is quite important, and that's pretty important for us when we try to characterize the product of the digestion going into milk. So, what have we done in DairyNZ with MOLY, with the original version of Baldwin, getting to DairyNZ MOLY version? Well, we have improved the lipid, glucose, and energy metabolism in conjunction with Lee Baldwin and Professor McNamara. So we used the improvement in our MOLY. McNamara was doing a sabbatical here a few years ago, and Mark Hannigan here is constantly working with us. So we have also improved lactation curves that better represent the reality of a dairy cow in New Zealand. Then Pierre Buques, my team leader, has developed an improvement of the effect of photoperiod in moly that also relates to lactation curves. And then I started working with Mark Hannigan in creating anabolic and metabolic hormones in a dynamic way in moly, just adjusting and improving the gestational metabolism in moly, and reparameterizing rumen and post-ruminal digestion parameters of moly, which give us a little bit more of accuracy and prediction in rumen fermentation patterns and products of digestion, nutrient supply, if you like, to the animal, to the host animal to produce milk or any other tissue, lean or fat or whatever you like. And then lately, and because of obvious reasons and because of the environmental concerns of the impact of agriculture onto the environment, we started to focus on methane production, improving the rumen of moly to better predict methane production total and methane yield, which took us to the latest development, trying to better predict responses in methane yield based on different levels of intake or different inputs of, I would say, dietary inputs to the rumen. So, and that's why we got into this improvement of moly, just better represent digestive outflow from the rumen of moly. So that's pretty much what we've done. You know, as you can imagine, it's not that easy, and it's, you know, took us around 20 years because, I mean, took us, you know, there's been work in DairyNZ before the 2000. The latest development in moly, as I just said, and because of the environmental concerns of agriculture and dairy cows, is the development of the representation of rumen digestive output from the rumen. So again, we are trying to get close to reality. Here you got again the scheme representing moly, and you got the rumen there. Well, by 1995, it was quite sophisticated. Then there appear some other rumen models like Anja from Jan Dijkstra in the Netherlands, Andre Banning. It's a more sophisticated rumen or representation of the rumen. So we were behind those models, and that's why we decided to improve the rumen of moly, again, to better represent some of the processes that allow us to design feeding management to have a less environmental impact, focusing again in this particular case in methane production. So what we did is add another pool into the rumen. We had originally large and small particles. Now we got medium particles, and these two pools are digested. The large particles can only be digested mechanically, pretty much just breaking down, not digested chemically or biologically. And once they are breaking down in size or digested chemically or biologically by the bugs, they are incorporated with solubles into the liquid phase of the rumen. And that will have an effect on osmolality, and osmolality plus rumination and water inflow coming from drinking water will determine, among several other things, the rumen digestive outflow. That's a very long story short, and if you like to read a boring paper, you can read the paper that I just mentioned. Yeah. So here you got the second graph of the paper, where you can say instead of feed intake, you can partition that feed intake in particular nutrients and how those nutrients go to different pools, and how those pools, you know, are determined by size from over 4.8 millimeters going to 4.8 and 1.2 and smaller than 1.2. These two are affected by digestion and are able to flow out of the rumen. However, the bigger one can only just go to the medium and small through mastication. So large particles cannot be digested. And the improvement here is that these small particles are being digested and can also flow out of the rumen. Before, only small particles could flow out. So that adds a little bit more reality, especially when you think that there are particles in the feces that are bigger than 1.2. So you say, oh, well, didn't you tell me that only particles smaller than 1.2 millimeters can flow out of the rumen? How they did flow out? Well, you can explain it from several angles, depending on how the particle dimensions flow through that little hole. But anyways, that's what we were trying to represent. Get the model more real, and even though those particles can flow out, they can also be fermented. And if they are fermented, especially because of the size, they tend to have a greater content of fiber and then potentially fermented to methane, or have the byproduct of methane production in the rumen. More into a acetogenic or non-glucogenic fermentation pattern rather than glucogenic fermentation pattern. These are one of some of the examples of how we improve moly, creating a little bit more or giving her a little bit more of reality in her rumen, things that we couldn't do before. In this particular case, forget about these low hunger and high hunger levels, because the actual input are different distribution of particles in the feed. These two low and high hunger levels was in the previous version of the paper, but I just liked the graph because it was in colors and it was quite easy to paste it in the slide instead of rebuilding it or copy and paste the one that I got in the paper. But anyways, this is correct, because with high level of hunger, the animals are going to masticate less, so they're going to be swallowing larger particles, right? So this is a different particle distribution that gets into the rumen. And with low levels of hunger, the animals, because it's not that hungry and they are not trying to compensate for the hunger, they pretty much masticate a little bit more, so the distribution of the particles that get into the rumen have a smaller medium particle size. So the input of the model in those particular graphs is different. Green, again, large particles getting into the rumen, and blue and dotted dashed lines are small, medium particle size getting into the rumen. So what we got here that is several variables. It's the outflow rate of organic matter, fiber digestion of digestion in the rumen, total volatile fatty acid produced, outflow rate of fiber from the rumen, microbial yield in the rumen, and methane yield, which is grams of methane per kilo of dry matter intake. And that's the x-axis. So we got all those variables affected by the particular particle size distribution at different levels of intake. And here we got what we wanted that moly couldn't represent before. It's like that methane yield decrease with greater levels of intake, and it's affected by hunger, if you like, or the particle size distribution of the diet. Previous to this development, we couldn't simulate that. And because of this development, we can think of newer designs that affect particle size distribution of ingesta going into the rumen and thereby alter the fermentation pattern, leading to more or less methane yield or production. Moly, it's a component model of the whole farm model. So in the whole farm model, which is a model representing the whole farm, we not only got moly and several instances of moly that can be initialized with different breeds, different genetic merits, different ages, different arrangement of moly initialized in a different way in a herd. So pretty much you create a virtual herd that interacts with crop models, with economic models, with weather models, etc. and etc. If we got time at the end of the presentation, we can click in there, the whole farm model, and you can see a little bit more detail of at least the face of that whole farm model. Whole farm model is being used almost for 2 decades in DairyNZ to design feeding management, farm management, design farms, and policy making. So for us, it's quite important to get the models we use for the farmers the most accurate and realistic as possible. This is one of two examples of how MOLY was used in the context of a farm, and in the particular case of improving production efficiency as a strategy to mitigate greenhouse gas emissions on pastoral systems in New Zealand. Also, we've used MOLY, again, in the context of the whole farm model to evaluate different feeding strategies, trying to reduce nitrogen discharges onto pastures. In that particular case, we were also evaluating the collateral effect of feeding towards reducing nitrogen excretion on a potential increase in methane emissions. That's pollution swapping. And I got a master's student now working on that pollution swapping, but she's going to be using the next model that I'm going to present, MINDY. So, from MOLY to MINDY. So that's the brief of MOLY and how we use MOLY, how MOLY has improved from her original version. And let's start talking about my beloved MINDY. Why we think of MINDY? Why we think of getting out of MOLY? Well, this is how I see MOLY. It is real, but not as real as we see the cows nowadays in New Zealand grazing around. And they don't feed on piles of grass. They feed on pastures. So that's why we thought of MINDY, because MOLY did not have a mechanistic and dynamic module of intake. Pretty much intake was an input to the model. MOLY is fed a mix of diet once a day, and that's it. The rumen liquid outflow is fixed, although we improve the representation of that digestive outflow. At the very end of the day, the passage rate of the liquid is fixed. It's a user input. In addition to that, the feed, the grass that is eaten by MOLY, doesn't change in time and space. We know that if you eat the top of the sward canopy strata, we'll have a different chemical composition than if the animals are eating the bottom of that. And we know that there is a change in the nutritive value because of photosynthesis, respiration, and transpiration from morning to evening. So there are changes in the feed through time and space, and that's what MOLY didn't have, and that's why we're thinking of incorporating into MINDY. MOLY doesn't show any preference, so she doesn't tell you what she would like to eat, and thereby doesn't have the capability to select between feeds. And also, when we talk about activity cost, the activity cost from an energy point of view in MOLY is fixed, or estimated by the oscillating finger rules. That's more or less. So we are trying to get an approximation from a mechanistic and dynamic point of view of representing those costs and try to see how much energy she expends, grazing, masticating, ruminating, or walking. These are new developments, and one of the latest ones is MOLY, although she can deal with other instances in MOLY in the whole farm model, she pretty much doesn't have any competition for feed. But MINDY now has the capability to graze a pasture with several mates and just suffer competition. If someone competes with her, the foraging strategy that she will implement to it will change. So several other things will change, not only from the input to the rumen, but also from the output production, or I imagine some excretion too, because of different rates of intakes, for example. So that's MINDY. So it's closer to the reality, and as I say, it's got rumen is used came from Molly, and we have improved it a little bit more, as you'll see later on, but also because she expressed preference and selection, she can think. Or at least we believe that we can say that she can think. These are the two papers so far that we have published documenting MINDY. The papers have most of the equations, but most of the equations have already changed because we are in a constant improvement of the model, and we want to get the model as a predictive model as soon as possible. The model is a scientific model that can be used to explore and to guide research, and has been going through conceptual validations and model verifications, but still, of course, lack of some operational validations that depends on the data. We are trying to simulate processes that are just demanded or pushed by different projects, and in that push and in those projects we are collecting data to have a kind of more iterative operational validation of the model. So, MINDY, who is she? MINDY is a mechanistic and dynamic simulation model of the diurnal feeding and grazing pattern of a dairy cows. Well, as you'll see later on, it's not only that, because we add several other modules. So it's a cluster of 5 models. Molly, the latest version of it, a soil canopy structure and herbage quality or nutritive value model, an ingestive behavior, a feeding motivation model, preference and selection model, and the foraging bioenergetics. So it's a cluster of models, it's not a single model. This is the schematic representation of MINDY. Here is the core of her. Well, she makes the decision whether to graze or not, pretty much feeding motivation. And that feeding motivation, is based on 2 kind of system stimuli. The external one, or incentives to graze or eat, and the long and short term internal system of stimulation. In the long term, you can have stage of lactation, genetic merit, adipositive, if you like, and in the short term, what's going on in the rumen, and some anabolic hormones like insulin. And those things end up in a kind of approximate representation of the ghrelin hormone that's going to tell how hungry MINDY feels throughout the time. The step of simulation of MINDY is 1 second, 1 minute, you decide. Depends on the speed of the simulation you want to run, but she can give you outputs at the level of a second, at the day, or lactation. Here you have a different part of MINDY that goes more into the ingestive characteristic: apprehension time, chewing time, bite rate, intake rate, bite mass, bite volume, depth, etc., etc. So some detail of the modules of MINDY is what I'm going to present here, and later on some examples of simulations to show how MINDY behaves. So this is how we represented the soil structure and quality as she grazed down the soil canopy. So here is a kind of geometric representation of the different grazing strata as she goes down, right? So you got an area of a bite, the depth of a bite, and as she grazes down, the bite depth will be reduced, following a rule of thumb of more or less 50% of the soil surface height. So bulk density change in space from the top to the bottom, or to the bottom to the top. You can build up an ideal harvesting architecture of the canopy, if you like, or represent whatever distribution of dry matter and nutrients, if you like. And also change, as I said, because of 3 processes related to the plant: photosynthesis, respiration, and transpiration throughout the day. Pretty much from dawn to dusk, there is an increase in the nutritive value of the herbage that she is able to graze. For example, an increase in photosynthesis, like soluble sugars that dilute fiber, protein, etc., etc. And that's why nutritive value changed throughout the day. Here is, like I was saying, how we represent small scale actions like the bite of the grazing pattern, the grazing process. MINDY also considers the length of the daylight and the length of the day. That's a photoperiod effect that have an impact, influence, or is taken into account that those external incentives to graze or not. So it's a part of the decision making. So if you add all of that and you think of MINDY like that, you can have a distribution of meals throughout the day. And also in green and orange, bouts of rumination. So MINDY also predicts rumination. So the first priority of MINDY is to go and eat. And she is satiated, she considers to ruminate based on the pool size of long particles in the rumen. So if she is not hungry and the pool size of long particles in the rumen is not big enough, she is not going to ruminate. But if she is ruminated and she gets hungry, she will stop ruminating and start eating again. Kind of summarizing the description of MINDY, so we using her, we can predict foraging dynamics or simulate foraging dynamics at different spatial and temporal scales that go from a single bite determined by mass and bite rate, residence time in feeding stations, what's the level of intake at each meal or grazing event, and what is going to happen at the daily level or bigger scale, at the paddock level. We can account for or just describe the locomotion all through what she rather eat at each particular spatio-temporal scale. She may be taking a bite of grass, but she would rather take a bite on a legume. And how long she's going to chew each bite, which will determine at the end of the day the particle size distribution of the ingest that is flowing into the rumen. So, at different spatio-temporal scale, as a result of ingestion, digestion, metabolism, genetic merit, and feeding context, MINDY can describe productive responses. Some examples to show you the capabilities of MINDY, and I guess this is the one. This is an example that is published in the paper. Or I'm not sure if this is exactly the one, but we face MINDY with this situation. So it's the daily grazing pattern and the interaction between cow genotype and grazing method. So we got here a continuous grazing method or set stocking. Pretty much they got shorter and dense sorts, and they don't have any particular area set. They can have unlimited area, if you like, to put it in a way. And you have two types of New Zealand cows, you know, the old biotype, 70s they call, and the modern New Zealand biotype, a little bit bigger cow, and the strip grazing method, just 24 hours pasture allocation. And I try in the slide to represent how those feeding contexts look like, as you could see. So, what MINDY say about it? Well, she said that if you are all New Zealand dairy cow under continuous grazing, you will eat 15 kilos. But if you are a modern one, in the same condition, you will eat 2 kilos more, roughly. If you are under strip grazing and you're an old New Zealand biotype, you're going to eat pretty much the same amount, which match what is found in the literature. So grazing method doesn't increase or reduce intake. And if you are a bigger cow, a modern New Zealand cow, it could be a little bit better to have constant access to a better quality grass through a different method instead of facing pasture depletion as you graze down the 24-hour break. She also predicts, different eating times and different rumination times according to the grazing method and the cow biotype. So this is telling us that Okay, yeah, we can start exploring the interaction of grazing methods and type of cows. You can initialize MINDY as a jersey, if you like, or you can change, as I said, the architecture of that particular soil canopy and the chemical composition as well. The responses in the grazing pattern and the nutrient supply from the rumen to the host animal are going to be different. Let's look at what happened throughout the day. Will she have the same grazing pattern? Well, we were quite happy to see that she didn't have the same one, so that means that our principles in the model were well set. So you have the grazing pattern of 2 cow biotypes under continuous grazing, and the grazing pattern of those 2 cow biotypes under strip grazing. The bigger cow, because she has greater demand of nutrients and she's hungrier, when we offer the new pasture break early in the morning, she will have longer meals. And that matched the data and the visual observations. It's quite obvious. So we were quite happy with that. And I should have said that in green is the meals, in orange the rumination bouts, and in gray island bouts, just pretty much other kind of activity. In light blue is the milking times. So we were happy with that, but the capabilities of MINDY allow us to ask a more detailed question. What was happening to you, MINDY, if you were a modern New Zealand cow and if you were grazed with 2 different grazing methods related to intake rates? So we can track the intake rate, which is in solid lines, for the different grazing methods and meals throughout the day. As you could see, in red is the strip grazing and in blue is a continuous grazing. Intake rate, distribution of the meal throughout the day, and intake rate within the meal changed because of the grazing methods. You can tell in the dotted lines, you can tell that, for example, the strip grazing one started with about 3 tons per hectare of dry matter, and she grazed throughout the day and ended up in about 1,500. That also gave us an idea that she was doing more or less what the cows do in reality. But as an explorative model, we could tell, okay, but tell me how many bites per minute you were taking, so factors that control that intake rate, so we can have something to explain why the things happen rather than only describing what happening. So, and then if you go into the locomotion dynamics, okay, tell me, MINDY, how many steps you've taken the first meal, and what's the walking or the eating step rate the same when you start eating the main meal and at the end? How did you take more searching step as the meal was progressing? Yeah, those kind of things you can ask MINDY. How many chews, seconds per bite you invested? So, and that it's quite important if you want to understand the rumen function, because it determines the input to the rumen, the particle size distribution. More is, like I was telling Bino today, that MINDY has the capability, she's got anabolic and catabolic hormones, but also the hunger hormone, which is a proxy of ghrelin. So we can tell that not only the level of hunger, but how it changed throughout the day is affected by the grazing method. It seems like under continuous grazing, cows are less hungry throughout the day compared to peaks of hunger or satiation of strip-grazed cows. And you can track, okay, the rumen concentration of volatile fatty acid, how it changed and relates to meal within the meal and meal distribution throughout the day, particular concentrations of ammonia in the rumen, or how the rumen was filled throughout the day. And you can tell that pretty much relate to the meal dynamics. And all of these data match the literature. As you can perceive, this is more like a model, scientific model that helps us to understand why things happen, and based on that, think of new, in this particular case, feeding strategies to feed particular set of animals. So MINDY also, as I say, is capable to express what she would like to eat. She'll tell you what she prefers. and based on that, she's going to make decision if she's got different feeds available of what to eat, selection. To do that, to represent that process and the pattern of that process is preference and selection. We integrate two theories, and I have the pleasure to work with Fred Provenza, Juan Villalba, and Mike Forbes in that. So we integrated these two theories, post-ingestive feedback theory and minimal total discomfort from Mike. So based on that, pretty much she's going to eat, she's going to have feedback loops based on what she eats. Let's say if she eats a lot of nitrogen, it's going to create a high ammonia concentrations, and that is a satiety signal, pretty much an uncomfortable feeling. Or if she eats something that create acidity in the rumen, she's going to go to pH lower than the optimals, and she's going to feel uncomfortable. So based on that uncomfortable feeling, she's going to prefer to eat some feeds that relieve her from that uncomfortable feeling. And if she's got those feeds available, she's going to go for that. And I'll show some example later on. I'm not going to go through all the detail of this flowchart diagram, but we got, here, preference and selection. And it's pretty much what I have just explained. Preference depends on the momentary internal state, how she feels at the time, feels between quotation, whether she needs more energy or more protein, less acid, more fiber, whatever. And what is the optimum feed for that particular momentary internal state? Based on that, she goes through satiety, total discomfort, how attracted she is to a particular feed, and then end up selecting if she's got a range or at least two feeds available. So if she's got something that is close to what she prefers, she would rather go to that than other feed that create discomfort. These are some examples. We challenged MINDY to an experiment that Juan Villalba and Fred Provenza ran years ago in 1999 with lambs. So we were trying to validate MINDY from a concept point of view. So this example shows that these 2 days, and we got the first day where we fed MINDY 5 meals of lucerne. Then we fast her overnight, and the next morning we face her to the challenge, which is either grass or barley grain. Lucerne got a lot of protein, grass has a high content of protein, and barley has low content of protein and high energy concentration. So what she did is, after those 5 meals of lucerne, and when she faced grass or barley, she chose barley. You can track in here the preference throughout those 2 days of different feeds in different colors: grain, soy, straw, and grass. And we can get here at the time of the feeding challenge, and by then the attraction or preference for grain was the highest, and that's why she went for the grain. The second option would have been the straw. Why? Because, probably provided more comfort. Well, but the straw was competing with the grass quite closely. So that's what she used at the time she needed to decide what to eat or not to eat. Let me know if I'm boring you, I can go faster. But this is another example, the opposite. So instead of 5 meals of protein, we feed her 5 meals of high energy concentrate, in this case maize. And we face her again to barley and grass after a night fasting. And when she faced those two, instead of barley, she chose the grass because she was overloaded with nitrogen. She was probably lacking of protein. And you can track before, you can say that when she was eating grain, she was quite attracted to straw. She was telling us, well, grain is okay, but I'd rather have a little bit of straw. Maybe trying to cope with acidity in the rumen. You can track that in the model and see if that, in fact, is the case. This is another example. And in here, we fed her 4 meals of lucerne, high protein content. We fed her to grass or barley, but we changed the timing of the day. So the feed challenge was around 6 p.m. and she had access again to barley and grain. And after the 5 meals of protein in the form of lucerne, she went first for the grain and then to the grass. So she's changing based on the internal state, on the minimal total discomfort and the post-ingestive feedback of eating those type of nutrients. This is the same thing as before. This is the last challenge that we put on MINDY when we wanted to see if she followed what Juan's and Fred's lambs did years ago. So in this case, we fed her maize, high energy content. We challenged her to barley, sorry, here should be barley, and grass, and she went for grass, then she rest and grass again, which makes sense and match what Fred and Juan found. You can track preference in that particular graph. So the other question was, okay, MINDY can represent preference, and based on the preference can select some particular feed. But will that preference and selectivity follow what the animals do in nature? This works with lactating ewes, lactating cows, heifers, and sarda ewes. I had the pleasure to work with Antonello Canas and Giovanni Molli a few weeks ago and discuss about this methodology that they used to determine diurnal pattern of selectivity in sarda sheep. Quite interesting. So what it happened is, like, in general, ruminants prefer to eat and then select legumes in the morning, and later on in the day they go for grasses. There are several theories around trying to explain that. One of them could be the minimal total discomfort or maximization of energy at early during the day because they feel hungry. So they try to maximize intake rate or intake energy. Yeah. So would MINDY show differential pattern of diurnal selectivity for grass and clover? That's the challenge we posed to MINDY. And in fact, she does. She does what the other ruminant do. She go for legumes in the morning and then grass in the afternoon. When we track that, we could see that the switch from one species to the other was dictated by the level of ammonia in the rumen. So one of the reasons could be that she was trying to balance the diet at that particular level, energy and protein. If we got time, I guess we are not going to have time, but I can open the model later on and show you more details of this run. So I'm going to speed up now. Another example was offering MINDY a mixed pasture the previous day. These are 2 days, time of the day in this axis, and then give her a breakfast in the morning milking of either soybean meal or barley, so protein or energy, and then face MINDY to a strip of grass or a white clover. As you can tell, depending on the breakfast she's got, either protein, soybean, or energy, barley, she will have a completely different meal in composition of rye grass in green or white clover in blue. So she's responding to her internal state. This kind of strategic supplementation can allow us to manage the grazing behavior or preserving some species or smash some species if we want to keep a particular set of mix or species in a mixed pasture. That could be one of the alternatives. But again, MINDY in here help us to understand why those things happen. And these phenomena have been seen not only in sheep, but also in grazing dairy cows in the States and Brazil. So conceptually it's validated. You can track the preference for those particular feeds or other feeds that she's got in mind, and she can have access. So if you know what she prefers, rather than offer what you got in the farm, you can say, okay, well, yeah, for a particular output, instead of feeding barley, I better feed her hay, or something like that. The model has that capability to help us understand what would be the best in terms of post-ingestive feedbacks, minimal total discomfort, and potentially rumen and outputs and productive outputs. So MINDY also account for energy expenditure while foraging. So that's the model of bioenergetic cost of activity. And also she can now, compared to Molly, graze with friends. This is the flowchart diagram of that model. I'm not going to go through all of that, but it considers the energy expenditure rate, of grazing, eating, ruminating, eating supplements, ruminating, locomotion, resting, etc., etc. At the very end of the day, we can calculate the instantaneous rate of energy expenditure and then integrate it over the day to estimate how much energy she would have spent with any particular farm management or feeding management. Small numbers can add up to big numbers when we talk about entire lactation. So when we are deciding to feed early lactation cow with the other full of milk compared to a light cow, it's not producing that much. This is one of the neat things that she's got now, is that she perceived friends that are competing for her preferred patches in green. So this is the area, just graphically represented, that you would allocate to a cow. But if you put another four cows with the same area allocation, and because of their gregariousness and the way of grazing, they most likely are going to compete for the proximate patches or feeding stations that one of them would prefer. So if MINDY here wanted to go to her preferred patch, she can't because there are some mates grazing there. So to do that, she will have to walk more. And in addition to that, she will change completely her foraging behavior that follows most of the optimal foraging theory. So integrates, walking, etc., and chewing, masticating will change. These are examples of that. Here it's MINDY grazing with 10 friends, the pasture mass or pasture cover of 3 tons per hectare, in an area of 100 square meters per day allocation to each cow. And the pasture was allocated at 7 a.m. That's in blue. In green is the same situation, but she's grazing along. And in black is the same situation, but with half of the pasture allocation. This is the instantaneous rate of energy expenditure and activity. And you can tell that she's going from the pasture to the shed, and from the shed to the pasture, and how much energy she's spending while she's grazing. And then back to the shed. You can tell in here the difference in rate of energy expenditure because she's full and has more milk in her udder. When she's grazing along, she spends less energy grazing because she doesn't have competition and she doesn't need to walk that much. And when she is grazing with the lower pasture allowance, half of that, she will have to deplete the sward canopy more, so she will be facing tougher pasture and thereby spending more energy while she is grazing. And that can be proved when we ask MINDY, okay, well now you are eating or you are grazing a soft pasture with low NDF contents compared with a tough pasture. Will your biting energy expenditure be the same? And as you can tell, it is not. And it changed even the length of the meal. So this can help us to explain, well, for example, why she is spending more biting energy here at the beginning of the meal if she is grazing a soft pasture. Pretty much because she could have higher bite rate. So the energy expenditure per unit of time of biting was higher. But then it changed. She satiated, and the other in the tough pasture she continued grazing and she expended more energy biting. So it helps us to explain why things happen. Similar thing with this with the situation of mastication. When she masticates tough pasture, she's going to spend more energy per minute, and thereby total energy of mastication at the daily level. Last but not least, in this particular development, we face MINDY to even pasture, if you like, in red, and a patchy pasture. Could be urine patches. So she faced two grazing environments completely different in the soil structure, a distribution of the preferred feeding stations or bites, if you like. So the walking energy, or the instantaneous rate of energy expenditure, changed based on the soil condition and state. Also the mastication. Because probably she's masticating bigger bites in the even pasture, she spent more energy masticating. The biting energy expenditure is greater in this type of environments because she'll have to keep biting. And all of that is translated into herbage intake rate. You know, those two different environments will lead to different intake rates. So she can have greater intake rate at the beginning of the meal in this more heterogeneous environment because she was probably preferring the more accessible part of the soil canopy, the taller ones, but once she depleted that, intake rate went down really fast. While in the other one, similar to a continuous grazing situation, she kept the intake rate throughout the meal. Also, MINDY can drink and urinate. This development was pushed by a quite interesting project that we are running in DairyNZ that is called the FRNL project, the Forage for Reducing Nitrogen Leaching, and how we are trying to minimize the impact of overgrazing management and systems onto the nitrogen footprint, if you like. So why it is we were looking at drinking and urinating through MINDY? Well, you'll see. We know that animals have a determined urination pattern. Just the urination pattern change during the day. It means the volume and the nitrogen concentration change. So that means that we got possibilities to capture that urine with high volumes or high concentration, and when we put cows in standoff, for example, and just reduce the discharge of that nitrogen onto pastures. This has also been documented in stalls in DairyNZ by Cameron Clark, where he found that the urine volumes change throughout the day and pretty much respond to feeding. The nitrogen concentrations of those urinations and the nitrogen, total nitrogen excreted throughout the day. So that presents us with an opportunity to manage urination behavior. So this is the module that we created in MINDY to represent the diurnal urination pattern, and we will depend on of course on the nitrogen content and the water content or the moisture content of the grass, what's going on in the rumen, where the water goes to, and the kidney function based on the dilution effect of blood urea nitrogen, which will determine the nitrogen concentration in urine. And this water flow, as you can go here, goes to the bladder, and things like bladder capacity, fetal size, and rumen fill determine the bladder capacity, and the trigger of urination that will end up in different volumes of urine that is integrated into the nitrogen concentration, and then we got the nitrogen concentration per urination event and distribution throughout the day. Wow, that was a long story, very short. Anyways, well, we use 8 published data set to parameterize the model, and we have a relatively goodness of fit. And we face the model to the first experiment of Keith Bittridge and see if MINDY behaved reasonably well. And we could predict pasture intake relatively well, the number of urinations, kind of okay, decently. We are still working on that, but I wanted to show you the work in progress. So with a 20% error, it's not bad for such a unknown process and pattern, if you like, because we still lack of data. And the urination volume, we are close in predicting it, and we didn't have data of mean nitrogen concentration, but the predicted one matched with the literature. That's average throughout the day. And also, we ask in that particular situation if that volume of urination events and nitrogen concentration change throughout the day. And we can tell that yes, it does. And that's what happened in nature. So MINDY is behaving in her urination pattern, if you like. We challenged MINDY to a different experiment. I'm not going to go through all the details, but we are comfortable so far with the preliminary parameterization in the model behavior. So with the predictions of intake, numbers of urinations, total water drunk, that told us that we could face MINDY to quite contrasting treatments. So we got a control treatment that I'll show now, and a 1/8 treatment. This means that in the control treatment, they have access to pasture the 24 hours a day. Well, pretty much 20 hours minus the 4 hours of milking. And the other, the 1/8, they only have 8 hours to graze between milkings. The idea in that experiment was to capture some of the urine to avoid urine deposition of nitrogen discharges onto pasture. So we asked MINDY, okay, well, we face you to that reality. Just tell me how you change the nitrogen concentration in this part of the graph, the upper part of the graph, and the volume of each urination event throughout the day. In yellow, we got the control one, and in red, the 1/8. So we can tell that not only the frequency, if you count the points, change throughout the day, but the distribution of those urination events throughout the day. And you can tell that there are some small difference that if you add that up at the end of the day or at lactation level, so nitrogen discharges into pasture can make the difference. So we were happy with that. So MINDY again can be changed, the grazing management, and simulate or predict different urination patterns. So what are the implications of that? If you look at that, you can tell, okay, 40% of the urinations that has got over 50% of the total urine volume with the highest concentration of nitrogen were captured in the standoff treatments at similar levels of milk production and similar levels of pasture intake. We didn't know that before the modeling, but the model now is telling what we were expecting. So you can use this type of models to better understand what have happened in the field and explain why did it happen. Last but not least, and probably this is the most interesting part for Stephen and Vinod, we were working in improving the digestive output from the rumen of moly. We applied that to MINDY, but we weren't completely happy with that. That's the improvement in moly, and now you're going to see what we add in MINDY. So in addition to this improvement in the rumen of moly that is used by MINDY, we have the effect of the harvesting apparatus, actions like rumination, salivation, oral processing, and particle size distribution based on factors of the animals or the canopy structure or the particular feeds, as well as the water drinking. All of that determine what is going to be flowing into the rumen and what the rumen is going to receive to be fermented and then flow out. More details on that, and because of Stephen and Vinod are interested in this part, how we determine the particle size distribution. This is zooming into those two boxes. So particle size distribution is a product of numbers of mastication job movements per bolus. And that depends on the bolus weight, and that depends on the time into the meal, hunger, fiber, and those three for each species also affect the saliva per jaw movement, and then salivation is also affected by apprehension, jaw movements per bolus, and those two depends on sword structure and biomass. At the very end of the day, the environment that she's grazing and the characteristics that environment, sword structure, fiber, and her internal state, hunger, for example, will determine the particle size distribution that is flowing into the rumen, and then fermentation pattern and nutrient supply to the host animal. So, thanks God, we got MINDY that help us to understand some of the little things that we cannot measure. At the same time, we are measuring some other things. Again, going to the in vitro, in vivo situation of digestion, ingestion measurements that we all want to take at the same time, but they are expensive. And quite long and expensive experiments can be run in MINDY in a couple of minutes. In addition to the, unfortunately, even the best experiments are merely snapshots in time of an ongoing dynamics, as my friend Fred said. The implications of all of that is not a replacement of reality. The models are designed to represent reality and complement reality, complement our empirical approach of science, to know and gain knowledge. It's a better tool to understand why rather than what will happen. Common, also, you can take MINDY as a common and heuristic tool. Like I keep saying, for explanatory research, greater definition and scope in designing mixed swords, as I explained with the preference and selection patterns, sword canopy structures, idiotypes, feeding circuits, differential feedings, toilet design, animal welfare, goal-oriented feeding management for DHD, 4-dimension high definitions, and beyond. The beyond one is like with Fred Provenza, we are thinking of using MINDY to evaluate human decisions in feed selection patterns. Because you can initialize MINDY as anorexic or as a diabetic, changing the parameters that control anabolic or catabolic hormones, or the effect of time of the day in hunger. So, having said that, thank you very much. And everybody knows that I'm a fan of Red Angus, and I like to put a picture of Red Angus at the very end. So, thank you for your time.
Thank you, Pablo. So one question I have is, clearly these models are quite complex and they have many parameters in them. Mm-hmm. So I think one particular challenge is, well, how do you determine those model parameters when you can only make a limited number of measurements? Yeah. And, yeah, that's one of the main challenges, especially in this area of the modeling. Most of the parameters that we use are based on literature. Yes, there are not many data, and we are collecting data. As I said, most of these developments are push from projects. So they have a particular question, and we say, well, we could make a development, the model, so we can help to explain that particular pattern or what you may get. So we use expertise for the unknown parameters from around the world. We got pretty knowledgeable people here in New Zealand, but as I said, you know, there were several people involved in the development of MOLY and MINDY throughout the world. So that's how we deal with that big limitation. But even in principle, you know, so some of the parameters like bite volume, for example, mm-hmm. is that something that can be measured?
And we got into there into what can we measure and what can we estimate. In my opinion, for example, we cannot measure pasture intake. It is impossible. We can estimate it, and there are several techniques that can get us closer to the reality. By volume is a hard one as well. How would you determine that? How are you sure that it's a cylindrical? We don't know. So as I said, it's an approximation, a representation of the reality. There are some indications and some other models that said, well, it may have a cylindrical form. So that's why we took it. And then you say, okay, well, is it working? Yes or no? Is this representation of reality good enough for the purpose of the model? Yes or not? If so, is that representation works okay within the context of that modeling exercise, or that model development? Yes or no? So that's how we deal with it.
I was wondering if you've looked at how cow behaviour is aligned with, I suppose, the output farmers are seeking. So let's assume dairy farmers are seeking maximum milk production from the feed supplied. When cows are able to select protein over energy or vice versa, is that driving that commercial outcome that farmers want? Have you looked at that?
No, I haven't looked at the commercial outcome, if you like. In the particular arena of behavior and the exercise that we run.
Efficiency, like are animals good at selecting the right food, the right type of food to eat for the output that humans are seeking?
Yeah, I mentioned that it will be no doubt that the animal will perform better. There is a good example of that in American feedlot. And the feedlot was even more weird because they have bisons in it. So, and they were faced to a TMR, total mixed ration, the perfect one, that the best nutritionists can formulate. And it's quite anthropogenic and anthropomorphic point of view, right? And then they offered the same ingredients but separately. And they decided the animals to choose. The ones that had the alternative to choose were more productive. Will that happen in a pasture environment? I mentioned yes. If you look at when you present the animals with the option of selection, or even in a monoculture, if you give it a big allowance, they can select, keep grazing the top strata rather than go down. That's selection at the very end of the day. So they will eat more and produce more. I like to look at this preference and selection point of view, or now the way I'm looking at it is like more from animal welfare. Will that be the future? Can we, start thinking of making animals feel comfortable with our particular feeding management? Also from feeding strategy point of view, the example that I gave, we are going to be, thinking, or we are thinking now in mixed pastures because they have different functions. For example, reducing nitrogen excretion and so on. But the mixed pasture will have a problem, which is how persistent are they, with the mix. So there's going to be some times that you need to be harder with the legume compared to the grass. So how you do that if you allocate the same area, if you like. So here we can show that managing the internal state of the animal will determine selections and preference. Or how can you manage that if you do some differential feeding? You got the alternative of getting the cows that get first to the paddock and eat the best. You got the alternative to feed them in a special way, so when they get to the paddock first, they are not that hungry, so the intake rate is not that high, so they leave more good grass for the slower ones. So those kind of management that may be, sound romantic or utopical now, but if we go back years ago, the management that we are doing now did sound like a kind of weird by then. So in the future, or maybe in other kind of systems, those concepts not only apply here, but can apply in some other grazing environments can be used. If you think of distribution patterns of the animals in big areas, in ranges, and you can locate some intensive grazing in some communities of plants, these concepts can be used. But again, I think we can use a lot of that here in our daily break of a ryegrass.
So I was just wondering, like, the sensitivity to some of these parameters. So like with light volume or that sort of stuff, and so you've estimated these values.
Mm-hmm.
But how sensitive are the outputs to the model if you underestimate?
That's a really good question. Most of them, and again, this it's a challenge. Most of them are quite sensitive. I mean, quite, and they are sensitive. You would say, okay, well, if I change the soil structure that provide a better harvestability, I mean, the herbage is more available and more accessible. So that will, let's say, create heavier bites, so higher intake rate. Yeah, the model is sensitive to that. How sensitive it is? I guess sensitivity enough. We ran a couple of sensitivity analysis for the first publication, and we only left the variables that actually have a good sensitivity. Also, we left some other variables that they weren't sensitive, that we thought, okay, maybe not now, but in the future we may have data that may help us to evaluate the outcome based on a range of input to that particular variable. So there are, and your question is really good, because not all of these variables are needed. The model could have been done much more simple, but because it's an experimental model, it's a scientific model, we thought that getting closer to reality will help us to explain things that we may not be able to explain with a simple experiment.
I mean, so one other thing. So for like, say, management strategies of supplementary feed.
Mm-hmm.
So have you looked at like what time of the day offering feed changes outputs, or so is it better to?
Are you kidding me?
Supplement after eating or during the middle of the day? Or,
but that's the other part of my work. I've been investigating that quite a lot, in fact, and I've been working in not only timing of supplementation. One of my PhD students just finished working on that, and I'll tell you a very long story short now. But I started working on that, the diurnal grazing pattern, and then just trying to match with the animals, the diurnal grazing pattern with the diurnal changes in pasture chemical composition. And just the timing of pasture allocation, and just through timing of pasture allocation, allocating the same amount, just at different times of the day, we can increase for free meal production or daily weight gain. I can give you a review article about it. It's quite strong. But then we start evaluating, okay, if they prefer to graze, let's say, in the evening or late in the afternoon, and they graze longer and more intense, why be bothering offering them pasture in the morning? That could increase their nutritive value. So we start playing off either fasting them before that evening meal, if you like, and see what happened. What we found is like grazing only for 4 hours in the evening produced the same output animal-wise that grazing for 24 hours. But they were saying, well, but they're eating more of the good stuff. So is really that good from an environmental point of view? Yeah, well, you can capture urine, you can reduce damage of the pasture, good. But digestively, they were less efficient because they were eating the same amount of dry matter, but with higher concentration of nutrient, and they produce the same. So we came to the conclusion that that could be a digestion inefficiency. So we start thinking of not supplementing the animal per se, but the bugs in the rumen, just trying to boost those little soldiers that are going to digest the grass. Because imagine that if you are eating at really high eating rates and you have a little number of microbes, they can't cope with it. So digestion was inefficient. So we think of, okay, let's supplement it. Not only to increase intake, because dairy cows are more sensitive, because require more, but if you are going to supplement, when? Right? And so I run an in vitro experiment in the States where we were simulating in continuous culture fermenters 4 hours of an intensive meal and feeding maize silage either 1 hour before or 9 hours before. 1 hour before, we got that theory of synchronization, energy, protein, and everything is going to be sweet and more. But the 9 hours before, which was what I was thinking, was going to feed the bugs, so at the time they face the intensive meal of grass, there are going to be more bugs to cope with the intake rate, high intake rate. What we found that supplementing 9 hours before the meal, morning milking, increased the glucogenic nutrient supply by 13%, milk if you like, and reduced the levels of ammonia and nitrogen in the rumen by 30%. So reduced nitrogen excretion. We weren't happy with that because that was in vitro, and I took a student with Grant Edwards in Lincoln that evaluated that in vivo. We found quite similar patterns. And in addition, supplementing before reduced substitution rate almost in half. 9 hours before compared to immediately before. So at the same resource allocation, you got greater outputs of the animal. That is technologies of process and patterns rather than inputs.
Okay, so let's...
I thought you knew the story. Thank you for asking that.
So let's call a halt there, and we've got some refreshments available, so you can chat more with Pablo over a drink. All right, thank you very much.
No worries.